All right, let's talk about one of the most daunting parts of the forces unit. This is problems involving inclined planes. For many students, this is where they really struggle. But I hope by the end of this video, and if you're taking careful notes, you'll see that the pieces of the inclined plane really aren't that bad. The part that gets tough is just remembering to use it. It's like this extra thing layered on top of all other force problems. So in an inclined plane, if we had a box like this sitting on a surface, I'm going to deal with it just without friction for now. So let me draw a free body diagram for this object. Oops, that's nowhere near straight enough. So there is the force of gravity acting on it, and then we know that it would also have normal force acting on it. Normal force would be at this angle because it always has to be perpendicular to the surface. What we see here is we have two forces that don't fall along the same axis. I can't say normal force and the force of gravity are equal. In fact, I can say they're definitely not equal because the force of gravity has to, it's not equal. But the problem gets worse than that because along the motion doesn't happen along an easy axis that involves the force of gravity. Motion ends up happening along here, along the surface of the inclined plane, and then we get no motion happening along this surface that's at a right angle to the surface, the one that the normal force falls along. Really the issue is if we try to use a conventional Cartesian coordinate system, we try and use like our positive y there and our positive x along the horizontal, we end up conveniently having force of gravity right along the y-axis, but normal force and all of the motion is happening at a diagonal relative to that. And that makes the problems very challenging to solve. It's doable, but you have to use trigonometry for literally every single step. And that becomes very taxing and makes the problems very, very long. So there's a better way to do it. And the better way to do it is to tilt our axis. What we're going to do is we're going to say, okay, this is the axis that we were trying to use, this Cartesian axis where we have force of gravity there and normal force there. Oh, I should mention, there's my angle right there. And since my surface is going down like this ends up being the exact same angle. So what's convenient to do is to just rotate this axis. And if I rotate that axis, it ends up looking like this. Let's do normal force as my first vector, just so I can try and make it look simpler enough. Okay, so there's our free body diagram. And I'm going to draw my new axis in green. And now normal force falls right along that axis. And if I was shifting my axis the way that I just did, by shifting it from here to there, I shifted it that many degrees away from the force of gravity, which means this is my new angle theta right there. So this ends up being a lot more convenient because now all of my motion is going to fall right along my x-axis. My y-axis has no motion happening on it at all, which means I can set up everything vertically on my y-axis as having no motion, being in equilibrium, and I can just do only have to do kinematics as needed along the x-axis. So it does simplify most problems to do it this way, but the problem that remains is, well, that isn't falling along the axis, so we have to break it into components. So this is the tricky part. I'm going to draw my triangle nice and big so I can show you all the pieces that make this work. And let's go back to drawing that free body diagram. Let's do it in color so it stands out a little bit better. All right, here's my force of gravity. There's mg. Here's my angle right there. If I draw my new axis along this green arrow here, there's normal force, of course, right there. Then what you should be able to recognize, if we go through a quick geometry proof, is that this right here is a 90-degree angle. If that's a 90-degree angle, then that means that this angle right there, I gotta use a different color. That means this angle right there must be 90 minus theta, must be the complementary angle to that one, because everything has to add up to 180. And if this is the complementary angle to that one, and this is also a right angle there, that means right there, that angle must also be theta. So it's actually getting really cluttered. I need to clean this up a little bit. So go back to that if you need to see that proof. But what I want you guys to remember is that this angle between the y-axis and the force of gravity is always the same as that angle. So if this is 30 degrees, that is 30 degrees. Then what we're going to do is we're just going to finish our triangle. And finishing our triangle is just going to mean that we're just going to turn this into a right triangle right here. I want this to be my hypotenuse, but that means I can break my force of gravity into a y component along this axis and an x component along this axis, which is parallel to the x-axis that we've been talking about. So if I do that, then you see that this angle here is m, or this side length right there would be the sine component, mg sine theta, and this side right there would be the cosine because it's adjacent to my angle, mg cosine theta. So these right here, this is what's going to be called our force of gravity that is perpendicular to my surface. And this one right here is going to be my force of gravity that is parallel to my surface. We're going to use these a lot, and I recommend that you memorize these or you write them down somewhere where you're going to see them, and you'll just use them over and over and over again until it becomes second nature, and then you'll just have it memorized. So these are the perpendicular and parallel components. And if I now wanted to write force equations, I want to write the sum of the forces in my x direction, that's this axis here, and the sum of my forces in my y direction, oops, that's getting kind of ugly. Sorry, I'll try and write nicer. In my x direction, the only force that I have is this one right here. So that would be mg sine theta. So this is not going to, there's going to be some acceleration here because we have an unbalanced force here. But in the y direction, I have normal force going up, and then I have going the opposite direction is the cosine component of mg cosine theta. And there's no motion that happens there, so they're in equilibrium. And that means that as long as there's nothing else pulling up or pushing down on this block, normal force is going to be equal to mg cosine theta. That actually becomes very convenient because we can use that a lot of the time to help quickly solve problems with force and friction along inclined planes. However, be careful because it will not work if we have static friction, not kinetic friction. So we'll talk more about that in our example problems and some of the work that we do with that. But there we go. We have inclined planes. We've talked about how we tilt the coordinate system, and we've talked about how we break the force of gravity into a perpendicular and a parallel component. So thank you for watching. Next video is going to be an example of how to do one of these problems.